In this video, we're going to discuss the full wave bridge rectifier circuit. So on the left side, we are going to apply an AC signal, that is an alternating current signal, to a transformer. Now to the right of this transformer, we have 4 diodes connected like this. And the way these 4 diodes are connected will allow us to convert an AC signal into a DC signal, which is the main purpose of a rectifier. So this is going to be the output of the bridge wave rectifier. Now let's put a resistor here. Let's call it resistor R. Now we have 4 points of interest. So let's call this point A, point B, point C, and point D. And this is going to be D1 or diode 1, diode 2, diode 3, and then diode 4 on the upper left side. And so this is the basic picture of the full wave bridge rectifier circuit. This is how it looks like. Now let's talk about the operation of this circuit. And so here is an AC sine wave, and during the positive half cycle of this wave, the top part of the right side of the transformer is going to have a positive potential, and the left side will have a negative potential. So that's going to be the polarity of the secondary side of the transformer. Conventional current will always flow from a high potential to a low potential. Now keep in mind, this is in the opposite direction of electron flow. So electrons actually flow in the opposite direction. So the green arrows will represent the flow of conventional current. So it's going to flow from the positive terminal of the transformer towards point A, and then from point A towards point B through D1. Now, is D1, is it on or off? Is D1 in forward bias mode or reverse bias mode? So anytime the direction of conventional current, if it's in the same direction of the arrow, the diode is on. It's active. It's on forward bias mode. Now let's say if the current is in the opposite direction to the arrow that's part of the diode symbol. In this case, the diode is in the off mode. It's not active. It's in reverse bias mode. So here we have the arrow, the direction of the current in the same direction as the diode arrow. So therefore D1 is on. It's active. It's in the forward bias mode. Now, will current flow from B to C? Is that going to happen? Notice that the arrow of the diode and the direction of the current, they're opposite to each other. So therefore, that's not going to happen. So let's put an X here. So we could say that D2 is off. So the electric current has no choice but to flow from point B through the resistor and then back towards point D. Now what's going to happen when it reaches point D? Will it go through D4? Because the current will be in the same direction as the diode arrow. Now, there's no point for it to return back to point A because it was already at point A. And whenever you see that, it's not going to work. And so D4 is in reverse bias mode. D4 is off. Another way you can think about it is to understand that the electric potential at point D is less than the electric potential at point A. Current will not flow from a low potential to a high potential. It doesn't work that way. Electric current will always flow from a high potential to a low potential. That is conventional current. So let's say that point A was at 20 volts. Point B will be at 19.3 volts. A typical diode has a voltage drop of 0.6 or 0.7 volts. Now there's going to be a voltage drop across this resistor. And let's say it's probably going to be 0.7. The voltage drop is really the difference between 19.3 and 0.7. So the electric potential at the other side of the resistor is 0.7. And going through D3, point C will be at 0, because that will be the opposite side of this transformer. So D is still 0.7. Current will prefer to flow from a high potential to a low potential, that is, from A to D. However, the arrow of the diode is opposite to the direction of that current, so it's going to be off. And current will not flow from a low potential to a high potential. It's not going to go from 0.7 to 20. And so that's not going to work. Therefore, either way you look at it, diode 4 is off. It's in the reverse bias state. It's not active. So once the current reaches point D, it's not going to go through D4. So that's not going to happen. Therefore, it has to go through D3. So D3 is going to be in the active state. Then from D3, it's going to reach to point C, and then it's going to go back to this transformer. And so that is the direction of the flow of conventional current during the positive half cycle. Now, let's focus on the resistor. We said that current flows from a high potential to a low potential. So the top part of the resistor is at a higher potential than the bottom part of the resistor. Now, in order for us to get DC current or direct current, the polarity of this resistor must remain the same for both the positive half cycle of the AC sine wave and the negative half cycle of the AC sine wave. So we see that it's positive at the top for the positive half cycle. Let's see if it's going to remain the same for the negative half cycle. So let me just get rid of some of the things that I wrote on this picture. Let's see how far this software will allow me to go back. So now, this is going to be the negative half cycle. So the polarity at the right side of the transformer will be reversed. The top part will have a negative sign this time. As always, conventional current will flow from the high potential towards the side with a lower potential. So it's going to emanate from the positive terminal and flow towards the negative terminal. So it's going to flow towards point C. And then from point C, the current will flow towards point B. That is through D2. And so D2 will be in the active state. It's not going to flow through D3 because, as you could see, the diode arrow and the direction of the current, they're opposite to each other. So D3 is inactive. It's off. So as current flows from C to B, it's going to pass through the resistor, going in this direction. So notice that the top part of the resistor is still positive, and the bottom part is still negative, because current will flow from a high potential to a low potential. And so therefore, the polarity across that resistor is the same. Thus, we now have a DC signal as opposed to an AC signal. And so the full wave bridge rectifier circuit is very useful if you want to convert an AC power source into a DC power source. Now let's continue with the flow of the conventional current. So it's going to flow towards point D. Now, will the electric current flow through D3? To answer that, let's put some numbers on the board. So we're going to say this is at a potential of 0 and this is at a potential of 20. So going from, let's say, C to B, there's going to be a voltage drop of 0.7, which means that the potential at B will be 19.3. And then going through the resistor, the potential is going to be at 0.7. And then going to point D, it's still at 0.7 because all we have is just a wire here. And so at point A, it's at 0. Point B is at 19.3, and at point C, it's at 20. So this will help us to tell which diodes will be on and which ones will be off. So now that the current is at point D, it's not going to go through D3 because if it goes in this direction, notice that it's going from a low potential to a high potential, and that's not going to happen. So once again, D3 is still off. Now it wants to go through D4 because the current is going from a high electric potential to a low electric potential. And so D4 will be on, it's active. Now once it reaches point A, it's not going to go to point B because you're going from a low potential to a high potential. And so that's not going to work. So D1 is off as well. So only D2 and D4 are active during the negative half cycle. Now once the current reaches point A, it's going to return back to the transformer. And so that's going to be the flow of conventional current in this circuit during the negative half cycle. Now what type of wave will we get at the output of this circuit? How will it look like? So at the output, we're going to get a pulsating DC signal that looks like this. And if we extend the AC signal at the input, it will look like this. So basically, the negative part of the AC sine wave gets flipped over the x-axis. And so this is going to be the output signal that we'll get for this particular circuit. So we have a pulsating DC signal, as you can see here. Now, when designing a power supply circuit, what you want to do is you want to get a nice, consistent DC signal. Ideally, you want a signal to be like this. You want it to be as smooth as possible. You don't want a pulsating DC wave. So how can we convert this pulsating DC signal into a more smooth DC signal? How can we do that? What elements can we add to this circuit to basically reduce the variations in voltage that we see at the output? Now, one of the first things that we can do is that we can add a capacitor parallel to the resistor. And the capacitor will basically filter out variations in voltages. So without the capacitor, we would have basically a pulsating DC signal that looks like this. But with the capacitor, the variations will be less. It will be more smooth, so to speak. So this is the positive terminal of the capacitor, and this is going to be the negative terminal of the capacitor. Now, let's focus on the picture. So when the voltage is rising, the capacitor is going to store charge. It's going to be in charging mode. And so it's going to absorb energy from the circuit. Now, while the voltage across the resistor is decreasing, the capacitor is going to release its stored energy to the circuit, thus preventing the voltage from dropping too low. And once the voltage is rising again, the capacitor is going to absorb energy again from the circuit, preventing the voltage from rising too quickly. And so by the capacitor absorbing energy and releasing energy to the circuit, it causes the voltage to be more consistent rather than falling quickly and then rising quickly. It smooths out the pulsating DC signal. Now the variation in voltages that we see here is called the ripple voltage. And you could reduce the ripple voltage by increasing the value of the capacitance or by increasing the load resistor, which you may not always have control over. Now you need to be careful when you're increasing the value of the capacitance in this circuit. Even though it's a very effective way to reduce the ripple voltage, there is another problem that you need to be aware of. So once you apply the AC signal to this rectifier, and if the capacitor is fully discharged, which it's probably going to be in that state, instead of current flowing through the device that's connected to this rectifier or even through the resistor, it's easier for current to flow through the capacitor because the capacitor will be charging. And so the capacitor will behave like a short circuit. Now keep in mind, conventional current really doesn't flow through the capacitor. It simply charges the capacitor because at the center of the capacitor, you do have an insulator. So just keep that in mind. So initially, the capacitor will be charging. Therefore, you're going to have a high current flowing in this region. And if that current is too high, it can burn the diodes. And so that current is going to be the peak voltage across the transformer minus the voltage drops of the diodes. So I'm just going to put V. And then divided by the resistance of the diodes plus the resistance of the transformer. Typically, these may be low values, so the current will be high. So this will be the maximum current that will flow through the capacitor while it's charging. Now we really don't have to worry about R because the resistance of these values will typically be a lot less than the load resistance. So how can we protect the diodes from the surge current so that the diodes don't burn out? Now granted, the surge current usually doesn't last long, so it may not always be a big problem. However, you don't want to go past the maximum rating of the diodes. So what you need to do is determine what your maximum peak voltage is minus the voltage drops of the diodes, which 2 diodes will be active at any point. So it's going to be the peak voltage across the transformer minus 1.4. And then you need to determine the resistance of the secondary side of the transformer and also the bulk resistance of the diodes. And thus you can estimate what the maximum surge current will be. Now one thing that you can do is use a certain type of diode. Some diodes have a maximum current rating of 1 amp. Others could be 10 amp diodes. Some can handle a current of 50 amps. And I've seen some large diodes that can handle 100. So that could be a simple way around that problem. Just use a diode that can handle a high current value. Now, if you don't have access to such diodes, what you could do is use a resistor, a series current limiting resistor. So let me redraw this portion of the circuit. So here is the series limiting resistor, and then here we have our capacitor and also the load resistance. So let's call this CRL, and this will be RS. So by adding RS, we can limit the amount of current that will flow through the diodes. Now you need to be careful because as you increase the series current limiting resistor RS, the output voltage will decrease because these two resistors, which I'm going to highlight in blue, they will form a voltage divider circuit. And so as RS increases, the output voltage of your rectifier will decrease. And so that's one disadvantage of using this series current limiting resistor. It will decrease the output voltage as you increase its value. So there's always some sort of trade-off. You can protect the diodes from the surge current, but you'll reduce the output voltage. So it might be easier just to use a diode that can handle a larger current value. Now there's something else that we can do. So instead of using that resistor, we can replace it with an inductor. Now the inductor will help us to have a constant current, just like the capacitor can maintain a constant voltage. When the voltage across the load resistor increases, the capacitor will be in charging mode. And so it's going to absorb energy from the circuit, thus helping the voltage to be constant. And when the voltage decreases, we know the capacitor will be in discharging mode, releasing energy to the circuit, thus supporting the falling voltages. So basically, putting the capacitor in parallel in this region allows the voltage to be held constant. When the voltage goes up, the capacitor will store energy in its electrostatic field. And when the voltage goes down, the collapsing field will release energy, thus maintaining a constant voltage. The inductor has the same effect, but rather than with voltage, it's with current. When the current goes up, the inductor will oppose this increase in current, and it does so by absorbing energy and storing it in its expanding magnetic field. When the current goes down, the magnetic field produced by the inductor collapses, and in that process, the inductor releases its stored energy back to the circuit, thus supporting the falling current. So basically, the inductor maintains an equilibrium with the current. It causes the current to remain constant, so to speak, whereas the capacitor allows us to achieve a state of equilibrium with the voltage of the circuit. So you want to use the inductor in order to maintain a constant current flow in the circuit, and you want to use the capacitor to maintain a constant voltage. And so this LC filter allows us to produce a very stable output. Now the inductor is very useful because it opposes any change in current. It doesn't oppose a constant DC current. So if we have a constant DC current, the inductor will not offer any impedance to it. However, if we have, let's say, a current that's constantly changing, it will oppose those changes. So therefore, the inductor, when placed in series with a circuit, will allow a steady DC current to pass with no impedance. However, it will oppose a pulsating DC signal. So thus, the inductor will help us to create a more stable DC output, which is what we want. So when designing an AC to DC power supply, you want to put the inductor in series with the output circuit, and you want the capacitor to be in parallel with the output circuit, or in parallel to the load resistor. So increasing the inductor, or the value of the inductance of the inductor, increasing the capacitance, and increasing the load resistance will help us to produce a stable DC output. Now there's one more thing that we could add to get a nice stable output voltage, and that is to use a Zener diode at the output. And since I'm running out of space, let's see if I can take this C and just fit it in here. So here is our Zener diode. And the purpose of the Zener diode is to maintain a constant voltage. So let's say without the Zener diode, we have a pulsating DC signal with, so not like this, but with the capacitor and the inductor. Let's say the signal looks more like this. We still have a small amount of ripple voltage. And let's say the highest point of this voltage is at 12.3. And the lower part of that voltage is 12.1. So let's say we have a DC signal that varies between 12.1 and 12.3, which means the ripple voltage is 0.2 volts or 200 millivolts. Now this is pretty good because we've minimized the ripple voltage. We don't have a pulsating DC signal like this. We have a fairly stable DC output, but we want to eliminate that ripple voltage. In this case, we want to use a Zener diode that's rated about 12 or 12.1 volts. But let's use 12 because that's a nice round number. Now let's say the voltage is at 12.3. If the voltage is above 12, the Zener diode will be active, and so current will flow through the Zener diode. Notice that the direction of the current is in the opposite direction of the arrow, and the Zener diode is designed to work in this way. It's designed to work in reverse bias mode. The breakdown voltage is 12 volts, so until you hit that number, the Zener diode will not conduct. So the bulk of the current will flow in this direction. However, some current will flow through the Zener diode if the voltage is above 12. And so what happens is, when the voltage is 12.3, a small amount of current will flow through the Zener diode. And as the current diverts in that direction, the voltage will drop from 12.3 to 12.2 to 12.1 and to 12. Once it hits 12, the Zener diode will not divert any other or any more additional current in this direction. So the remainder current will flow here. So it will continue to abstract current until it brings the voltage to 12, at which point it's not going to pull any more current away from the circuit. So therefore, the result of all of this is that we're going to get a nice, steady DC signal at 12 volts. And so the Zener diode is very effective at capping the output voltage at 12. Anytime the voltage is above 12, like 12.1, 12.2, 12.3, it's going to pull current in this direction, bringing that voltage back to 12. That's giving us a nice stable output voltage. So that's it for this video. Now you know how to design an AC to DC power supply, and you also know how to produce a nice steady DC output signal by using elements such as the inductor in series and the capacitor and Zener diode in parallel to the load resistor. Thanks for watching.